No. Okay. So welcome to Math 383 Complex Analysis. And today we're going to be doing lecture 7. And the lecture today is going to be on a lot of things. Oh, interesting. So some of it seems to be missing. We're going to do Holomorphic is analytic, Cauchy's inequalities. We're going to do Liouville's theorem, which leads to the fundamental theorem of algebra. And then we'll try to do some integration examples as much as possible. And so again, this is a graduate level class. And so if this is the first graduate level class you've taken, it is a bit of a adjustment. We are not going to cover every line. A lot of times I'm going to refer you to the book for a lot of the details. If you have questions, let me know. Talk to me. If I'm in my office, it's office hours. Talk to the TA. I can work some of the stuff into the class, but I'm expecting you to be able to read the book and follow most of the proofs. What I want to do is I want to try to emphasize the big ideas. Why do we argue the way we do? Why is this a reasonable thing to do? For some of the calculations, they're almost presented just directly. Let's choose this contour. How did we come to that? And we talked a little bit about this when we were looking at the function, I think 1 minus cosine x over x squared, as to how we came across with using this for the integrand and this for the contour. That you actually have choices. And that's where things get interesting. The more choices you have, the harder it is. If you factor a quadratic, you can do it by just divine inspiration, by looking at it and say, oh, it's x minus 2 times x minus 3. But if you are not divinely inspired, is that the end of the world? No, what do you use? Quadratic formula, quadratic equation. You can solve it easily. It's not as fast if you can just look at it, but you have a go-to that you can use. Fortunately, for a lot of these problems, there's only a couple of things to try. And you just try a couple of them and see which ones work. Okay, so we are almost done with the hellish part of the semester where it's never clear exactly what have we proven. We're almost at the point where we're going to just say we can integrate and we know what the answer is. So last time we proved that if you have a holomorphic set and an open set in a disk, but what we really just need is that the entire interior of the curve is contained. And the reason why we're doing this is a little bit hand-wavy is because you then have to prove that if I give you a simple closed curve, that it divides the plane into the interior and the exterior. And if there's some real topology that's going on. So rather than proving the theorems in full generality, I've just sketched what you need to do and just referred to here is what is needed to make it rigorous. But if I give you a nice region, you can just verify directly that it works for this. And then it becomes a question of defining what is nice. And to some extent, nice is I can deform one curve to another if they share the same endpoints in the space. And I can't do that if I have a donut. I can't pass through the donut if there's a hole in the center. All right, so we have f of z is 1 over 2 pi I, the integral along the boundary curve c of f of zeta over zeta minus z dz. So what's beautiful about this is the value of the function in the interior is completely specified by the value of the function on the boundary. All right, and whose theorem is this? Yeah, I don't know if it counts if somebody else says it, if it only counts if I say it. And so just, it does count, anybody has to say, okay. All right, so I will not repeat what was said, but yes, that is the correct name. Then we have a bunch of corollaries from that. One of the corollaries is that if your function is holomorphic, well, let's just take derivatives. And this proves that your function is infinitely differentiable. And we even have an explicit formula for the derivative in terms of the integral. And if you've seen the debate between Professors Adams and Garrity about the derivative versus the integral, hopefully this can lead to peace in our department and you stop these fractured, horrible, horrible disputes that are tearing us apart. They're really equivalent. Another corollary we talked about was the Cauchy inequalities. I'm not sure it's really fair that he gets credit on a recap, but that the nth derivative is basically bounded by essentially the sup norm of the function on the curve. We have an n factorial divided by r to the n. So the further out you go, the larger r to the n is down below. But of course, maybe the function is growing on the boundary of the curve. So when I write this, it's not clear how strong of a bound this is because I need to know something about how rapidly the function is growing. But if somehow we knew that the function wasn't growing that rapidly, then this is going to give us strong information. For instance, what if I tell you that the function is bounded? What's this going to tell you about the derivatives? Yeah, they have to be 0. So we'll see some tremendous consequences of that very shortly. Right. So theorem 4.4. So suppose f is holomorphic in an open set omega. If D is a disk centered at 0, and whose closure is contained in omega. So again, basically saying, nice region, I have the interior, and I have a little bit beyond the curve as well, so I can do anything I need to. I have a power series expansion for my function. My function is analytic. It's given by a Taylor series. Not only is it given by a Taylor series, but it's given it in a constructive way. I can actually tell you what the, by just using the formula from the previous page. The nth derivative at z is just the integral. I can just use that. So that's absolutely beautiful. So what this is telling us is that if you are differentiable once, you're infinitely differentiable, and you're given by your power series expansion. And remember, this is not necessarily true in real analysis. The function e to the negative 1 over x squared is infinitely differentiable, but all the derivatives at the origin is 0. So it doesn't equal its series expansion. Complex analysis is quite different. The proof is actually pretty straightforward. A lot of it comes down to what can you do legally, what you have to really justify. If we go back a page to trying to prove the formula for the nth derivative, well, if I just take n derivatives and say the derivative of the integral is the integral of the derivative, then we're done. You need to be able to justify that. Or you can go back, as we talked about, to the definition of the derivative, look at f of z plus h minus f of z over h, and then just argue. So you can, if you don't know the rules about when can you interchange a derivative and an integral, you can prove it the long way. Or physics, and it was good that somebody does have their physics hat today. You put on your physics hat and you just interchange the orders. But what's going on over here? Well, I want to try to argue, similarly, and try to prove that I have a series expansion. It should not come as a shock that I'm starting with the fact that f of z is given by this integral. And now I want to somehow convert this. And the key idea is to add 0. So we look at 1 over zeta minus z. That's the key part in the integration. And we write this as zeta minus z naught plus z naught minus z. And because I've added and subtracted z naught, I haven't done anything. And I'm going to break it into 2 parts. I have the zeta minus z naught, and I have the z minus z naught. So let's think about what's going on. So here is my circle C. Here is some point z naught. And then here's some point z that's close to z naught. And I'm choosing some little ball about z naught that's entirely contained in my circle. And so again, all of these concepts are local concepts. I'm doing a series expansion near z naught, so I can assume z is very, very close to z naught. In particular, z is going to be closer to z naught than any point zeta on the unit circle. Oh, I'm sorry, on the circle C is going to be. Because we're assuming that the disk about z naught that contains z is entirely contained in the circle. So any point on the boundary of the circle has to be further away. So that means that the absolute value of zeta minus z is going to be greater than the absolute value of z minus z naught. And so when I look at the denominator, I can pull out a zeta minus z naught, and I just multiply by 1. And so I'll get z minus z naught divided by zeta minus z naught. So this is good. We're multiplying by 1 and we're adding 0. Right? We're doing everything in this problem. And now we just use the geometric series. We just expand this out. And when we expand this out, we'll just get z minus z naught over zeta minus z naught to higher and higher powers. And when we look at this, it's going to now look very similar to this, except what we'll have is we'll have f of z is 1 over 2 pi I, the integral, I'm not sure why they say I over there, we're using c, we'll say c. Then we have f of zeta, and then the 1 over zeta minus z becomes this, we have a 1 over zeta minus z naught, then we have a sum, n goes from 0 to infinity of z minus z naught over zeta minus z naught to the n d zeta. And that's what we get from just using the geometric series expansion. And then what do we want to do at this point?
pull the integral and pull the sum out?
Yeah, we want to just pull the sum out of the integral. And if we pull the sum out of the integral, then essentially the definition of f of z naught. And so if the integral of the sum is the sum of the integral, we get f of z is 1 over 2 pi I, the sum n goes from 0 to infinity, the integral over c, f of zeta over zeta minus z naught to the n plus 1 power, d zeta. And then we have z minus z naught to the n. And that's essentially the series expansion we need. We're missing the n factorial, not a big deal. Multiply by n factorial, divide by n factorial. If I put in an extra n factorial, I apologize, but it's roughly like this. So we need to justify the interchange. Why is the interchange legal? So why does the integral of the sum equal the sum of the integral?
Everything's finite, we can fill between.
No, because everything is not finite. I'm sorry? It's not that it's a linear operator, because again, we have an infinite sum. So as soon as you have infinite sums, you have trouble. So you have to look at absolute convergence. Yes, yes. And that's essentially what you need to do. You now need to use the fact that these are getting very small, the function is bounded. And you can just show that if you put in absolute values, you can use the Houdini thing. So when you put in absolute values, you're fine. Put in absolute values, use z minus z naught over zeta minus, was it z naught? And absolute value is strictly less than 1. There is a trick that you could do if you want to bypass some of these technicalities if you're interested. So I'll just say, here is a trick. Does anybody know what a stable distribution is from probability? So a stable distribution is when you take two random variables that have this distribution, their sum also has that distribution. Anybody know an example of a stable distribution? Yeah, Gaussian. Gaussian plus Gaussian is Gaussian. It may not have the same mean in the variance, but it's still going to have the same shape. Cauchy plus Cauchy is actually Cauchy. It's another stable distribution. Uniform plus uniform is not uniform. If you have a fair die, you get the numbers 1 through 6. You have another fair die 1 to 6, and if you add them, you get 2 to 12. You get 7 1/6 the time, and you get 2 and 12 only 1/32 of the time. It's going to be like a triangle. So it's very rare to get a stable distribution. A geometric series has a really nice property. If I give you, g of x is 1 plus x squared plus plus x to the n plus x to the n plus 1, going all the way up to infinity. So this is the sum, little n goes from 0 to n of x to the n. And what do you notice about the tail? It's a geometric series. So I can write that as x to the n plus 1 times, g of x. So if you want to do the analysis, I can actually avoid having to deal with an infinite sum by saying that the sum of the tail of a geometric series, it's a geometric series again, and I have this factor now x to the n plus 1 outside. And if that is less than 1, if I raise it to a huge power, that's a lot less than 1 now. And so you can actually bypass the finite, the infinitude, and make it finite. So can do everything as a finite sum with error. And so this is worth noting that you have this special trick that you can do with a geometric series. If you want to prove that you can differentiate term by term, this is a nice way to do it. It's not going to be applicable for other things. This is a very special proof, but it's nice to know sometimes that we have special proofs. All right, so the next is Liouville's theorem. And so this is nice to have somebody other than Cauchy and Riemann making the list, but Liouville will not be on it that often. All right. Liouville's theorem says if F is entire and bounded, so entire means defined in all of C. So this is defined on all of C, then F is constant. That is a remarkable result. Is this true in real analysis? If you have a function that's defined on all of R and is infinitely differentiable, then it must be bounded. All right, give me a counterexample. Sine of x, another one. Cosine of x, yeah, is one thing to say that. The Cauchy distribution, 1 over 1 plus x squared. We have lots of examples in real analysis of bounded functions. There's another one which you've already mentioned a couple of times today. Yeah, the Gaussian, either the negative, oh, I'm sorry. Either negative 1 over x squared works. I was actually thinking of e to the negative x squared of the Gaussian. There's lots of examples of functions. So what is so different about complex analysis? It turns out that complex analysis, the functions you can look at is a very restricted set. To be differentiable is such a strong condition that so many functions that you would normally be able to study are just gone. Right? Any thoughts about how we would prove Liouville's theorem? Yeah, Cauchy inequalities. And that should not count as 2. Is it counting as 2? Okay, thank you. This should be so like, if you say the word in, 2 quick succession, it doesn't count. Cauchy inequality. Oh, it's just I say it. Oh, okay. So we know that the nth derivative of our function at some point z in absolute value is less than equal to, we had the sup on the curve C divided by r to the n. Was there a 2 pi? No, it's an n factorial. And then we have times n factorial. I don't really care about the n factorial because that's fixed. So here's the origin. Here's my radius r. Here's my curve C. And because the function is bounded, well, I know the sup norm is at most some fixed constant. So as bounded, we get that the nth derivative is less than equal to some number b times n factorial over r to the n. And where does that go to as n goes to infinity? So if n gets very, very large, what does b times n factorial over r to the n go to? Does it always go to 0? When does it not go to 0? Well, r is the radius. Oh, sorry. I don't want n going to infinity. I'm sorry. I want r going to infinity. My fault. I want r going to infinity. As the radius gets larger and larger and larger, what is this going to go to? Now it goes to 0. Are you sure? Good. So it goes to 0 unless n equals what value? 0. So, well, that's not so surprising. If n equals 0, we're just talking not about no derivatives, it's talking about the value of the function. And then that basically just gives us the value of the function is bounded by b. Wow, what a shock. If the function is bounded by b, then the function is bounded by b. True, the function is bounded by b. But we actually proved it out using the Cauchy inequality. All right, so not really that useful when n equals 0. But when n equals 1, this is now useful. We now know that the first derivative is identically 0. So f prime of z equals 0 for all z. What does it mean if the first derivative is always 0? F has to be equal to z. So implies f is constant. If f is not constant, then there's got to be some change in it at some point. And so we now immediately deduce that f is constant. So a remarkable result. Yes? We're told that f is bounded. So that's one of the inputs to the problem. We're saying it's bounded by, say, b. And so if the function is bounded by b, then it actually has to be constant. And we don't know it's actually that value b. We're just saying it's constant. I'm not saying it equals b. Because we know the function's entire. As soon as we know it's differentiable once, we just proved it's differentiable infinitely. Although technically for this, I actually don't need that it's infinitely differentiable. I only need to do this for n equals 1. I don't need to know that it's differentiable to degree 2 or 3 or 4. I'm only using n equals 1. Any other questions? Yes. Okay, but if you, as soon as you say piecewise function, you're going to lose differentiability. It depends on how things match up. So again, there's differences between how things match up in terms of real and how things match up in terms of complex. And you might be able to match things up nicely for real to have the first derivatives work out. But if the function has two different values where it differs, you're not going to have the first derivative 0 everywhere. You know, think of it as, you can just integrate along the curve. And think about maybe, f of z is I integrate from z0 to z of f prime, f prime of zeta d zeta. And then I'll add in f of z0, right? I have a primitive to f prime of zeta, it's just f. And when I integrate this, I get f of z. And so if the first derivative is identically 0, then the only possibility is f of z equals f of z. We're using f as entire so we can take out exactly. And so if you only know that you are bounded in a region, that doesn't give you anything, which is not surprising. If I take the function z squared plus z to the 1701, and I look at a disk of radius 5, it's bounded. So not surprising. All right. So now we're going to get every non-constant polynomial with complex coefficients has a root in c. What's wonderful about this is if you try to solve polynomials with integer coefficients, you lose. Not every polynomial with integer coefficient has an integer root. So for example, if I want to solve 2x minus 3 equals 0, we get x equals, if I've done it right, 3 halves, which is not an integer. So if you look at polynomials with integer coordinates, that's not enough to guarantee that your roots will be integer. Well, what if we look at polynomials with rational? Well, we get rational back. I could look at x squared minus 2 equals 0. That implies x equals plus or minus root 2, which is not in the rationals. Okay, so it's not enough if I just start off with a polynomial with rational coefficients that my roots will be rational. What if I just take real coefficients? I could do x squared plus 1 equals 0. That implies x equals plus or minus the square root of negative 1, which is not even real. And so unfortunately, these fail. And given failure after failure after failure, it's not unreasonable if you start to think, well, if I start looking at polynomials with complex coefficients, maybe I'm going to have to expand beyond the complex numbers to solve. And that's where things are amazing. Add the square root of negative 1, which is I, and enough to solve any polynomial of the form, an z to the n plus a0 equals 0 with the aj complex numbers. Why didn't I say with the ai in complex numbers? We don't use i's as a subscript in this class. Okay, if you want to make me upset, so this is for the people who really know me. What can you do to make me upset? No, actually, it's related to that. Support the yin. What tech thing can you do that will make me livid? The cardinal sin of tech.
Hard label stuff?
Hard label an equation in tech. All right, that will make me furious because if you then add anything before, all the numbering changes. If you really want to make me upset in this class, use I as a subscript. Right? It's just, it should not be done. We don't do that in flight. Right? We are on the way of proving that. So the first thing is that if I give you a non-constant polynomial, then it has a root in C. Is it necessary that the polynomial be non-constant? Yes. If I give you the function, f of z equals 5, I don't expect to be able to find a z such that 5 equals 0. So it's a reasonable assumption. That's all we need. Any polynomial with complex coefficients has a complex root. What do you think we're going to get immediately from this? Yes. Yeah, the fundamental theorem of algebra follows immediately after this. That if I give you any complex polynomial, I can just factor this. And the reason is you can just keep decreasing the degree by 1. Since it has a root, factor out the root, z minus w1. You now have a polynomial of slightly lower degree. That has to have a root. Keep going, keep going, keep going. Yes? I'm sorry? Oh, so if I know f of z naught equals 0, I want to write that as z minus z naught times g of z. And so I need to be able to show that z minus z naught goes into both. So then the question is just how much rigor do you want for something like this? So we have z minus z naught is clearly going to be a root on the right-hand side. The question is, if we do polynomial long division, so we've got, z minus z naught. How many people remember polynomial long division? It's almost like the, days when you have the newborn baby, you kind of forget those days as you get older. But the memories are there, an z to the n plus an minus 1, z to the n minus 1 plus dot 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 plus a0. And we start doing the polynomial long division. So what's the first thing we have to put in? It would have to be, an, z to the n minus 1. We would get, an z to the n minus an z to the n minus 1. We subtract, and we would get an minus 1 minus an z to the n minus 1. Pull down the a n minus 2, z to the n minus 2, and continue. And so when we continue doing this, we're going to get stuff coming out over here. And then when we finish over here, we have to have a 0, because otherwise it would not have a 0 at z0. So this is polynomial long division. We actually have now finally used this. So it doesn't say this on the slide here, so I'm going to put it in red. This is the, I did choose red. Try choosing red again. This is the fundamental theorem of algebra. There's lots of proofs of the fundamental theorem of algebra. This is one of the fastest. It really shows you the power of complex analysis. We don't have that many fundamental theorems. This is not like the participation awards that we give everybody nowadays in sports. Then, congratulations, you showed up. Here's a participation award. We don't let any theorem just call itself fundamental. Yes? So that's an interesting question. I mean, what we are calling here is, it's actually a corollary of a corollary in the book, if you really want to go. And the real thing is Liouville's theorem. So it's really Liouville's theorem that has as a corollary the fundamental theorem of algebra. So the fundamental theorem of algebra is by itself a major result. In terms of what we're doing for complex analysis, it's a corollary. It puts it in place. In terms of it shows you just the power of complex analysis. It's remarkable if you look at some of the other proofs of trying to prove the fundamental theorem of algebra. It is absolutely worthy of the name fundamental. And it's one of those things that when you see it, it's quite hard to prove. It's intuitively obvious that if I have a polynomial degree and it should have n roots, and then you start thinking about, well, wait a minute, if I give you a polynomial like, x squared plus 4, x squared plus 4 has no real roots. All right, I can complexify and I can see kind of what's going on, but how do I know that when I start putting in complex coefficients, 2 plus I times z squared minus, square root of 7 minus 3i z, stuff like that. How do I know that's going to have a root? It's remarkable that once we introduce the square root of -1, nothing else is needed. All right, so now we've shown that the fundamental theorem of algebra follows from this. We now have to show this, that if I have a polynomial that's not constant, then it has to have a root. So let's assume that there's no root, because if there's a root, it's trivial. Assume no root, go for a contradiction. So let's study f of z is 1 over p of z. And this is something that we can only do because we're assuming our function has no roots. What can you tell me about this function? It's bounded holomorphic. So you are correct. Of the two things you said, one of them is much easier to prove than the other. Which is the easy one to prove? Nope. So holomorphic. So why is it holomorphic? Has no roots, so we can actually just differentiate 1 over p of z. Just use either the power rule or the quotient rule, and everything is fine. So holomorphic is easy. Bounded, a little harder. Okay, so how would we prove that it's bounded? So here's 0. Here, as always, is my circle of radius r and some curve. Now, if you look at the polynomial, as n gets very, very, the a to the n, z to the n is much, much larger than everything else. So for z sufficiently big, the an z to the n is going to be greater than or equal to twice the absolute value of every other term, an minus 1, zn minus 1, plus dot dot dot, plus a0. And the reason is an is not 0. This has one more power of z. So if you just look at how much everything could be, the best case is if you have complete alignment. And I have an minus 1 and an minus 2 and all the way down to a0, they all have the same sign, they're all real numbers, and I just add them together. So if you take, I think r is greater than maybe 1,000 to be safe, absolute value of an minus 1 plus an minus 2 plus a0 plus 1 divided by maybe the absolute value of it. I think something like that should work. But if you take r sufficiently large, this is going to be much larger than everything else. That's just a nice exercise to show. Essentially, the function is going to infinity. The z to the n term is eventually going to dominate. It's going to dominate by a significant amount. Okay. Well, since that's going to infinity, then that means eventually there's going to be some limit when I look at the reciprocal. It's going to be getting smaller as I go further and further out, right? Because if p of z is going to infinity, then 1 over p of z is going to 0. So as the absolute value of p of z goes to infinity, as the absolute value of z goes to infinity, then the absolute value of f of z goes to 0. And so now we have a continuous function. If you choose R, a continuous function on a closed bounded, continuous function on a compact set. What do you know about a continuous function on a compact set? Uniformly continuous. What else do we know? It attains its max and it attains its minimum. Well, I don't really care about the minimum today. I care about the maximum today. So the function is going to be bounded in the disk. And then as we go beyond the disk, it's only getting smaller. So this does lead to the function is bounded. So f of z is bounded. And now we have an entire function. So it's holomorphic and it's bounded. So what does that imply? Sorry? So we have an entire holomorphic function, an entire bounded function. So as f is entire and bounded, what do we know about f? F is constant by Liouville. By Liouville, f is constant. And that's a contradiction. What is it contradicting? Close. Our assumption, right? What was our assumption? Well, so is it contradicting our assumption? So it says every non-constant. So we assumed that our function is not constant. And now we just got, so you're saying that n is 1, I think is essentially the same. Yes. Oh, okay. Okay. So, right, so we might need to do a little bit of the laws of logic here. We just showed that if we have no root, then our function must be constant. But we know our function is not constant. Therefore, we must have a root. All right, so now we've proven 4.6. We immediately get 4.7, which is Liouville, implying the fundamental theorem of algebra, which is absolutely wonderful. Okay. So now it's time to do some integration examples. So let's do some integration examples. Now there's a lot of different ones we could do. Let's integrate negative infinity to infinity of dx over 1 plus x squared. So I'm not doing the sine of x over x because that's in the video and you can just watch that. So we need to complexify that. So how many of you remember the integral test from Calc 3? You know, I give you a series and we compare that series to an integral. If the integral diverges, the series diverges. If the integral converges, the series converges. And you have to figure out what function to use for the integral test. Usually it's really obvious. You replace n with x. So we need to complexify the function 1 over 1 plus x squared. Does anybody want to give me a guess for what a good complexification would be? 1 over 1 plus z squared. So here, it's pretty straightforward that this is what we should look at. For other problems, it's a little bit harder. When we have sines and cosines, we actually have a couple of ways we can do it. And sometimes it actually helps to add on an odd function which integrates to 0, because that helps with which exponential we can have. This is a nicer situation. Now, if we look at the function 1 over 1 plus z squared, where are the places where it's not holomorphic? Yes. Z equals I, anything else? And negative I. So there are 2 points we need to stay away from. But if we integrate along the real axis, we're okay. And so the way you normally do these is here's minus r, here's r. And with decent imagination, here's a hemisphere. Okay. And we integrate along a curve like this. And if we look to see where does the function blow up, here's I, and here's minus I. So we have 1 point of difficulty that's inside the region. And so what we would want to do, when we're integrating along here, is, we would, be coming down like this, come up, go around, come back, and continue. And if we do something like that, we reduce the integral over the region like this. So the integral over this is equal to the integral over the green circle about I. Is everybody comfortable with that? This is the standard Cauchy argument. Eventually, we're going to clarify this and extract it as the Cauchy residue formula. But essentially, what we do is we just cut out that little region. We now have a nice place where the function is holomorphic in the entire interior, and they're going up and going down around I cancels. We're going around the point I clockwise. How dare we? We have to go in counterclockwise. That's how we always do things. But that's good because the integral over the big semicircle plus the counterclockwise integral is 0. So that means the integral over the semicircle equals the integral over the full circle. And so now let's think about what's going on. If we integrate along the boundary from minus r to r of f of z dz, that's just the integral from minus r to r of dx over 1 plus x squared. And that's exactly what we want to get. So that part is no problem. That's exactly what we want. Now we need to do the other part. What is the integral over the semicircle part? So let's call this S of r. So now, what is the integral over S of r of f of z dz? Let's bound that. What's the length of the curve? What's the length of the semicircle? Yes, pi r. And what's the maximum value of the function? Almost. What is the largest absolute value? 1 over r squared minus 1. The worst case for us is if z squared is negative r squared. So the value of the function is 1 over, worst case, r squared minus 1. And that's going to go to 0 as r goes to infinity. Because I've got r in the numerator and I've got r squared minus 1 in the denominator. The denominator kills it. Well, no, we're doing absolute value, right? I'm looking at what is the absolute value of the integral? It's at most the length of the curve times the largest value of the integrand. And so we know that part goes to 0. So it basically says the integral of this is just equal to the integral along I. All right, so now we need to do that. So here is I, not drawn to scale. Here's a small circle about I. So I want to integrate about a circle centered at I of the function 1 over 1 plus z squared dz. Okay. We've reduced this to a very nice problem. So now we just have to figure out how do we do this. So this is in some sense a little bit of a preamble to finding the Cauchy formula to figure out these integrals. What could we try to do? We could write z as I plus, say, epsilon e to the I theta. Right? Or we could try to put all this in and just do the integration. Let's try to think about what's going on. So I can write this 1 over 1 plus z squared as 1 over z minus I, 1 over z plus I. We agree with this? As z gets very, very close to I, what does 1 over z plus I look like? Yeah, it looks like 1 over 2I. So there's really no problem from understanding the 1 over z plus I. The 1 over z minus I, that's the more interesting piece. So near I, 1 over z plus I is approximately just 1 over 2I. Okay. And so what we're really doing is we're going to do like a Taylor series expansion about the point I. The 1 over z minus I is looking really good. If I didn't have the 1 over z plus I, I would just be integrating 1 over z minus I about a circle centered at I. All of this I can do getting the function 1 over z centered at the origin. I've just shifted things. So I just have to deal with the fact that I don't have just 1 over z minus I. I'm multiplying by 1 over z plus I. Well, I can play some games. I like playing games. 1 over I plus z is 1 over I plus I minus I plus z, which is 1 over 2I plus z minus I, right? Which is 1 over 2I, 1 over 1 minus, I guess it's 1 plus, z minus I over 2I. Yes? And now we can just expand it by the geometric series. It's 1 over 2I, and then we'll have a sum, and goes from 0 to infinity of negative z minus I over 2I, because I have a plus sign on a minus sign to the nth power. So it's going to be 1 over 2I plus, nice. So I'm just playing some games to see what the expansion is going to look like. Well, now when I hit it with a 1 over z minus I, all of the nice stuff has at least a z minus I. Has at least a z minus I. So if we divide by z minus I, it's still holomorphic. So what we get is 1 over z squared plus 1 is 1 over 2I, 1 over z minus I, plus a holomorphic piece. And now when we integrate over the circle, we'll have a 1 over 2 pi I. Oh, actually, I don't think I have the 1 over 2 pi I. Like this. Of our function f of z dz, this is going to be the integral over the circle about I of 1 over 2I, 1 over z minus I, dz, plus the integral over ci of something holomorphic. What does this integral equal? It just equals 0. What does this integral equal? Yep. So this is going to be 1 over 2I times 2 pi I, which is equal to just pi. Hello? Are you here? And so we get pi, and so when we put the pieces together, we get the integral from minus infinity to infinity of 1 over 1 plus x squared dx is equal to pi. So we actually proved this without using the arctangent. And what I want you to think about is, can you do these integrals? And if not, why not? We could do this when n equals 2. Can you do this for any integer n? Can you do it for any rational n, any real n? What can you do? Can you do this without complex analysis, or do we fundamentally need complex analysis? So this is a good place to start. Have a great day.